Okay, let's get started. So we are focusing on dimensionality reduction today, and the main two dimensionality reduction technique are the. So is it audible first of all? Is it audible? Hello. Is it audible? Uh, Maybe you can unmute and tell it yourself. Is it audible? No. Yes. Something. Okay, let's continue. We're focusing on dimensionality reduction. Okay, uh, there are two main ones, that is principal component analysis and linear discriminant analysis. Okay, so first we'll cover some theories and then we can focus on the questions and applications. Okay, uh, so we'll go through the slides there is. Okay, so as you can see, so the dimensionality, as you can see, the problem first of all is that uh, this at a specific dimension, the classes may not be separable. Okay, so there is a problem of separability. Okay, the data sets converge. Okay, overlap. Okay, so this is the overlap, as you can see, this green area. uh, okay, so that happens. Okay, and so many a times if you take it to a lower dimension it may be separable. Okay, so one problem is that with dimensionality, at a higher dimension it is not easier to separate two classes. Okay, two or more classes. Okay, so that is the problem of separability. Okay, and this g function, as you can see, is the so if you can see multivariate normal distribution here. So this is the multivariate normal distribution, and here as you can see, this is the PDF of that. Okay, so this is the PDF of the distribution. Okay, and what we are doing, the function we are analyzing uh, is this uh, logarithm of the uh, PDF of the normal distribution. Okay, so okay, so here what I want to represent to you is that this uh, so there are total n summations while calculating the sample mean that we have used here. Okay, another is the sample covariance here. Okay, and so there are uh, so it is in the it is in the it is proportional to d square dimensions. Okay, so as you can see, the computational it becomes computationally expensive when the dimension increases. Okay, so we have got few algorithms to reduce the dimension. Okay, to improve separability as well as computational efficiency. Okay, so so that is what we are focusing on. So there are two types: principal component analysis and LDA is there. Okay, so first of all, going towards principal components. Uh, so as you can see, so uh, so there is this. We have calculated the mean. Okay, and from the mean. Okay, and mean follows this line. Okay, means first of all, so this is the mean. Okay, and this x is the any number they have okay, and this a is the error, associated error. Okay, uh, so so this is what we have got as the error function. Okay, and as you can see, so this is the loss function. Okay, as they have opened the uh, as they've opened this error, the square, what you call this L2 norm square. Okay, so we have opened this L2 norm square in like this. Okay, and so this is our loss function. Okay, taking derivative with respect to this a vectors. Okay, so what we get, a as this. Okay, so this is the orthogonal projection of xk uh, along this E transpose. Okay, so that value is called AK here. Okay, so that is the component we have here. Okay, so that is how we define principal components here. Okay, so that is the orthogonal projection on a vector E. Okay, and we always first of all normalize the data. Okay, normalize the data. So this is what we have. Okay, so in univariate situation we do it like this. Okay, and next we progress on to multivariate case. Okay, so for multivariate case what we have here is the uh, this. Okay, so how do we define this? uh, so we have this so we have defined the loss function like this. So first of all, so if you understand the first expression here, so this x any vector here. Okay, okay, is defined as the mean vector plus a times a times a this e vector, which is the eigenvector. Okay, uh, so that is how we have represented it. And from the univariate case, coming to the multivariate case, as you can see, we have come to that like that. And okay, okay, so this can be this is the our covariance matrix, while it is also called the scatter matrix, which shows the variance of the data. Okay, and okay, so this is the loss function we have. Okay, and we need to minimize it. Okay, so and this condition is there, this it is a unit vector. Okay, so value of that is equals to 1. Okay, so we have used Lagrangian lambda. Okay, and so this is our what you call cost function or objective. Okay, so we uh, minimize the objective, as it's a minimization problem. Cost, we have to reduce the cost. Okay, and as you can see, first so so this is the higher dimensional derivative vector calculus things. So as you take derivative of E transpose like this. Okay, where S is a positive definite matrix. Okay, so this reduces to 2SE, and so it is a classical eigenvalue problem. Okay, and so maximization of this quantity. Okay, this is E transpose SE. Okay, where E is a where E is the eigenvector. Okay, so that reduces to a eigenvalue problem. Okay, so it is same as eigenvalue decomposition, as you can see. uh, okay, so we can conclude that principal component analysis, we are actually taking out the components with the maximum eigenvalue. Okay, uh, okay, so that is it. And okay, so nothing more to address here. Okay, so little more from the next slides. So this is the same one. Okay, so this is like a more exquisite section that we have. So uh, Karo-En lower transformation. Okay, KL transformation, which is actually a very simple thing. Okay, so what we are doing is like we are taking the data set into in such a operation, like we are taking it to a space of orthonormal eigenvectors. Okay, so the dimensions in that space are uncorrelated. Okay, and dimension is also reduced. Okay, so that is we'll see the significance of that. Okay, so as you can see, mean and covariance is defined. Okay, as you know it. Okay, and next so okay, so this is the situation we have. Okay, so what transformation matrix we are going to use? This is the transformation matrix A we have defined. Okay, which is the uh, means the each eigenvectors. Okay, are stacked in the rows one after another. Okay, so that is why you see E1 transpose, E2 transpose, like that. Okay, up to how many eigenvectors it has. Okay, whatever that will be the dimension. Okay, um, okay, so this is the transformation. Okay, after the transformation, the new variable is y. So it's a very simple problem actually. Just you need to have good knowledge of stats and linear algebra. I hope it is simple for you. It is for me at least. Uh, so so as you can see, it is supposed to have mean is 0 and covariance is this. Okay, so I have so you can see the derivations as well. Okay, uh, so okay, so this transformation is followed. Okay, and next, the most important here is that so after transformation, the covariance matrix, the off diagonal elements are uncorrelated. Okay, so it is a so they are all and okay, so that is it. Okay, so the eigenvectors are orthonormal, Okay, after this, so just after PCA they will be orthonormal. There we are using that, just that one. Okay, uh, so so that is it. Okay, and some application vision, as you can see. So we have this image, two-dimensional data. Okay, what we are doing is that first we are taking it to a to the we are carrying out this transformation. Okay, and and such that we are going to a lower dimension. Okay, then we can come back to the previous dimension, but okay, we are using AK this time. Okay, the number of principal components that we desire to take, k principal components is what we desire to take. Okay, uh, so that is what we are doing. Okay, and so what will happen, as we are taking only k principal components in reconstruction. Okay, so that will result in some information loss. Okay, uh, and that will result in reconstruction error. Okay, so reconstruction error is the defined as this. Okay, so the principal components that we have neglected. Okay, the eigenvalues that we have neglected. Okay, some of those eigenvalues. Okay, that is defined as the reconstruction error. Okay, and we minimize it such that we get to an optimal value. Okay, so this is it. Okay, mm, okay, uh, so this is it really, and so that is how you can decorrelate the dimensions of, okay, in that new space Y. Okay, uh, so that is what we have. Okay, next next is that next maybe we should focus on the problems first. Okay, uh, so first question is this. Okay, uh, so as you can understand by now, the principal component is the largest eigenvalue of the scatter matrix. Okay, or the sample covariance. Okay, so we have to solve the eigenvalue problem here. Okay, to get the answer. uh, so what we're going to do now is I'll show you. Okay, okay, I'll show you step by step what to do in such a situation. So as you can see, so this is what we have. Okay, so we need to find the S matrix. Okay, which is nothing but the sample covariance. Okay, so how do we find the sample covariance? So let me show you. uh, so sample covariance is this, right? uh, Sample covariance S, which is the unbiased estimator here. Okay, is I equals to 1 to n summation of xi minus mu I and xi minus mu I transpose. Okay, so this is it. This is the our sample covariance matrix. Okay, so mu I, as you can see, is 0, minus 3, minus 1, minus 4, and this is 4. Okay, so this two-dimensional 0 vector. Okay, okay, so this will simplify into xi transpose I equals to 1 to n 1 by n. Okay, and how much is this? Okay, so if you can see this, it will be minus 3 minus 3 minus 3 minus 3. Okay, so this is the multiplication, row by column. Okay, so what is this? 9. Okay, this is what? 9 again. This is 9 and 9. Okay, so for first sample we have this. Second one what we'll have is 1 1 1 1. Okay, third one is again 1 1 1 1. Okay, and fourth one is 9 9 9 9. Add this up. Okay, 9 2 times 18 and 2 is 20. Okay, so our sample covariance matrix is 20 20 20 20 and we have to divide it by 1 by 4. Okay, so the sample covariance matrix becomes 5 5 5 5. This is sample covariance matrix. Okay, S, and we need to solve the eigenvalue problem. Okay, lambda minus 5 square equals to 25. Okay, so lambda minus 5 plus minus 5 lambda equals to 10 or 0. Okay, so so this is what we have. Okay, so this is our thing. Okay, so principal component is needed. Okay, so coefficients AI are the principal component. Okay, so let's find that. Okay, okay, so what we have is that it is E transpose, as you can see, xk. Okay, so from lambda we get which dimension is important. So first one is more important. As you can see, lambda for 10, we will calculate that. Okay, uh, okay, and what we have here is that we need the eigenvector. Okay, so if you progress from here. Okay, so what will you get here is that so to find the eigenvector, what we're going to do is for each value of the eigenvalue, so this becomes 10, so minus 5 5. Okay, and x1 x2 equals to 0. Okay, so what you get here is that one is 1, another is minus 1. Okay, normalizing it is this. Okay, so this is it. We've got our eigenvalue and eigenvectors. Okay, and eigenvector will be means this component will be uh, transformation of xk onto this eigenvector. Okay. Um, okay. So E transpose is this 1 by root 2 minus 1 by root 2. Okay. And let's see xk, right? So xk, what will be here? It's a feature vector. That's right, it's a feature vector. Okay. Uh, so, okay. So feature vector, as you can see, these are the one. Okay. Uh, okay. It will be two-dimensional, that's for sure. Okay. We'll come back to this problem later. Okay. And so next problem we go into. Uh, so uh, next problem is actually big one actually. Okay. Okay. Next problem. We need to come to problem. Done. So next problem. So in PC, as you can understand, the principal components are orthogonal to each other. Okay. In the direction of the orthonormal to each other. Okay. And not orthonormal, orthogonal only. Okay. And the direction is towards the eigenvectors. Okay. So this is a vector. Okay. So as you can see, four-dimensional 0.5. So you have to check whichever it is, means orthogonal to, means like dot product should be equal to 0. Okay. So that is how the 3 and 4 satisfies. Okay. So if you can see, if you take the dot product, it is 0.5 in positive and then 0.5 in negative. Okay. Similarly like that. Okay. uh, so that is how we do this question. Okay. Okay. Next we are on to LDA. Okay. And so So LDA, as you can see, is this. So it's a very nice diagram we have got here. Okay. Uh, so as you can see, with PCA, what we are doing, we are separating them. Okay, we are increasing the distance. Okay, between the two classes. In LDA, what we are doing is that we are increasing the distance between the mean. Okay, uh, but maximizing the eh, variance within each class. Okay, so within each class we are increasing the variance. Okay, so as you can see, this is the best example. Okay, so mean is like this. Okay, so we have distanced the two mean first and increase the variance so that they can gain a more distributed shape. Okay, so like that we have done. Okay, so that is it. Okay, and okay, so these are the different dimensions. Okay, m dimensions samples. Okay, total n samples. Okay, we have, and so we write this transformation y is equals to w transpose x. Okay, why do we need this? Because we need a transformation. Okay, such that they get to this shape. Okay, okay, that should be easy to understand. Okay, and so this is the projection vector w. Okay, so so we need to find the optimum w that we denote by w star. Okay, so for that what we are doing is that we are writing the mean for mean before projection and mean after projection, so it is the same. Okay, means not same, mean after projection is w transpose mu I initial. Okay, so first objective function is distance between the two means. Okay, and this is w transpose mu1 minus mu2. Okay, and okay, so this is it. Okay, and the variance we have defined as the uh, error. Okay, error with the mean. Okay, and it is defined as si square, as you can see. So some of the errors. Okay, some of the variances. Okay, so jw is this. Okay, and so this total is called sw here within class scatter matrix. Okay, and and okay, so you have to understand this one first. Okay, so what they have done is that they have taken this w transpose square is there, so w transpose here, w is there. Okay, and this can be represented as the transpose square in multi-dimension can be represented as the quantity and the transpose of the quantity multiplication of both. Okay, and as the w's are not dependent on the summation. Okay, or not dependent on x, so they have come out, and you can write it like this transpose form. Okay, and so similarly we do it. Okay, and we're able to sum up. Okay, and this is the sw uh, sample covariance matrix. Okay, and next what we have here is the next what we have here is this. um, so first of all what we have is, so this before so as you can see, uh, this difference can be represented as like this. Okay, and this sb is the between class scatter of the is before the transformation of the original distribution. Okay, and F for SB bar, it is the after the projection. Okay, so that is what we have got. So that is what we're doing. Okay, so this is the the form of the loss function we have. Okay, and the process, you can see we have maximized. Again it gets to a generalized eigenvalue problem. Okay, and w transpose, w star is defined as this. Okay, uh, okay, as w inverse mu1 minus mu2. Okay, so in this problem, as you can see, question number 2, it is what we need to solve here. Okay, the one similar problem is there in the slides only. Okay, so we're going to proceed like that. Okay, okay, but easier problem is this one. Okay, this question number 4. Okay, so they have asked the what is the between class scatter matrix. Okay, so that is easier. So I will show you just some multiplication and you get it actually. Okay, so for that, okay, so for that, so as you can see, between class scatter matrix is this one, right? SB, what was it? Okay, SB. So we need to find SB here. Okay, and it is this. Okay, so mu1 minus mu2. Okay, and transpose of that like that. Okay, so 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 what are the mu's? Okay, so this is 3 and 5, and this is 6 and 8. Okay, okay, so this is it. Okay, and first we need to take difference, right? So 6 minus 3 is 3, 8 minus 5 is 4. Okay, and okay, and this is 3 and 4 itself. Okay, so we multiplied 3, 3 9. Okay, 3 4 12. Sure. Acha, sum is there, right? 50 data points. Acha. Okay, okay, okay. So what we get here is that, so this matrix is the one. Okay. Between class scatter matrix, yeah, it should come out. Let's see. So 3 4 12, 4 3 12, and 4 4 16. Okay, so that is what I am getting, and the answer is not the same. Let's see. Covariance matrix is given between class scatter matrix. If I'm not wrong, this is the one, right? Between class scatter. Okay, maybe they're asking for something else here. Okay, so covariances they calculate first. So that is what is there. Okay, but maybe they're asking for something else. Between class scatter matrix. Between class scatter matrix. Yes, this is the one. Between class scatter matrix. Okay. I do here? Anybody has solved this problem? Barugula, you've done. Actually, I think it is the old one. If I open the new one, NOC, this is the one. Okay. In question number, this is the one, right? Assignments. Okay. The same questions, I think. You have solved this one. Four number question. Question number 4. Uh, what are they asking? Maybe they're asking something different. Maybe they're asking for SW here. Calculate SW here. So it is the sum of the covariance matrices, right? Yes, a sample covariance matrix. So this is so so it is the sum of the sample covariance matrices, right? Uh, okay, right. So 9 and 12 is 21. What are they asking here? So hard to understand. 21, 4 and 3 are 7. It will be symmetric, so 7, and this one will be 8 and 6, so that is 14. Okay, and if we progress further, so this is SW we have got. Maybe they are asking for SB cap one. I think that should be the one after transformation. Okay, so there is lot to that. Then as for SB cap unit transformation with respect to W here. Okay, so first need to find W. Okay, uh, okay, as you can see here, so SB bar is the between class scatter in the projected samples Y. Okay, so for projection we need to find the W. Okay, okay, which is defined as like this. Okay, SW inverse and this. Okay, so let's find SW inverse here. Okay, so this is SW, that must be the one, I think. So SW inverse is the adjoint. Okay, okay, adjoint of A upon determinant of A. So the 7 comes out. Okay, okay, let's do it then. 21 into 14 minus 7 square. Okay, and dividing by 7, what we get here is 2 minus 1 minus 1 3. Okay, and and the rest what we have is 3 into 14 minus 7. Okay, so for 3 12, 42 minus 7, this is 35. Okay, this is our inverse. Okay, SW inverse. Next what we have here is mu1 minus mu2 difference. Okay, so what will it be is actually I have done it wrong here actually, that is what came wrong actually. Okay, 5 or 8 is 3. Oh, I got it actually already. Okay, so mistake here. Okay, 5 or 8 is 3 here, so if we multiply it will come out 9. Okay, okay, this is the answer, right? So you got it actually. Nothing more was required. That is what they asked. Okay, so this one was done. Okay, some calculation mistake derailed the solution. Okay, but for this question we need to do a lot of calculation. Okay, and so let me show you how it is done. It's not required. Okay. Okay, so what we're doing here is that first we need to find the mean. Okay, okay, so mu1 is the mean here, and it comes out to be, as you can see, 5 and 6 by 2 15. Okay, 15 first. So mu1 is 15 here, and this is 10, 16, 18, 18 by 5. No, mu1 is not 15, divided by 5. Okay, so this is 5 here actually, 5 here, and this is 10, 16, 18, 18 is there, right? 10 and 16 and 2, 18, 18, 18 divided by 5. Okay, so this is mu1, then we calculate mu2 here. Okay, and this is it, 11 and 14, 19, 24, 28, 28, and next is 6, 9, 12. Okay, divided by 5 has to be there, just mean. Okay, so this is it, right? And mean we have got. Okay, covariance is even more difficult. Okay, so covariance you can do, I guess, the sample covariance S1 and S2 you can find. Okay, from that you have to get SW, that is the sum of S1 and S2. Okay, then W is what they've asked for, W star actually. Okay, which is equals to SW inverse X mu I minus mu2. Okay, so this is it, right? And okay, so this is what you have to do. Okay, calculation is long. Okay, so not doing it, but you can do it to get the answer. And so last we have, now we go to the these questions. Okay, so which seeks direction that are efficient for discrimination. The direction we are seeking in the case of PCA, right? Okay, so it will be PCA. Nothing much, just theory here. If all the eigenvalues are same, then PCA will not be able to select principal component. Okay, That is the answer, right? Yeah. Because as you can see, principal component has the highest eigenvalue. Okay, so if the eigenvalues are same, then it not be able to choose a component. Okay. Okay. Next question actually. So so if it is if it retains k principal component, then dimension t decreases, right? It's a very simple question actually. Let's start. Okay. Okay. So the standardization of the data is important for applying PCA. Okay. So this last part actually is the answer of this question. Hmm. Because as you can understand, we are when while calculating, it has to be uh, the covariance and everything has to be zero mean, right? So that is why standardization is important. Okay. Uh, okay. So this is the answer. So maximize within class variance. Okay, and minimize between. Yes, that is the one, right? Maximize within class variance and minimize between class variance. The goal of LDA. Okay, so that's the one. Hmm, that's the one, right? Okay, so that is done. Next is number of linear discriminates equals number of classes. Okay, simple in LDA. Okay, so this is it actually, and go back to the first problem actually. Let's see we have done the calculation right or not first of all. uh, so mean is 0 here. Okay, so this is what it becomes. Okay, and this is okay. So this becomes 9. Okay, addition will give you 20. Okay, so 20 I've written here, and divided by numbers, that is 5. Okay, 5. Acha. Okay, okay, got it wrong. Number is 4, I think, not 5. Or is it 4? 5. Number is 4. Okay, so we get 5 here. Okay, so this is our matrix. Okay, scatter matrix. And we are solving this eigenvalue problem. Okay, in which we get this. Okay, this plus minus 5. 5 is added. Okay, Okay, so 5 is added. Achha, I got it wrong actually. So if 5 is added, so that becomes 10. Achha, minus 5 is there. 5 is achha, no problem still. Okay, so 5 and 0 are the 10 and 0 are the eigenvalues. Okay, next what we have is we're looking at the eigenvector. Okay, so if we solve the eigenvector problem, so this is what it becomes. Okay, and as you can see, these are just the clear opposite of. Okay, so okay, so it will be like this, right? Or maybe to better show you, what will be what will it be, minus x1 plus x2 equals to 0, and x1 minus x2 equals to 0. So same, right? And what does it mean is that, which I've got it wrong actually, x2 is equals to x1. Acha, so this is the eigenvector actually. This is the eigenvector 1 1. Okay. And to normalize it, okay, so this is the one. And okay, and we need to find the principal component. Okay, and so so this is the principal component. Okay, xk. Okay, 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 got it. Okay, uh, so uh, this does not look correct actually. Do not compute principal component for each sample. Okay, here that is what they have shown actually, right? Right. Okay. Okay. So let's check out actually. Okay. So eigenvalue problem is solved. Okay, eigenvectors we have got. have done actually. Eigenvalue comes to be lambda 1, right? So that is 1.28. Okay. uh, but answer is not that right. So we'll have to see what the problem is actually. Maybe I'm doing it correctly, but answer is wrong here. Okay. So this is where we finish actually. So this is the week 7 done. I'll look at this problem. Okay, if the question is wrong or I'm doing it wrong. Okay. Uh, okay. Thank you very much, people. Thanks for attending. Okay. Uh, okay. Thank you very much. Bye.